Hello and welcome to today's webinar from Ricardo, North America. This is the third in our series of technical webinars, and today we're looking at the future for commercial vehicles, so future truck, and the requirements and powertrain architectures that will be necessary to meet the challenges coming forward in the future. My name is Chris.brockbank and I'm Vice President of Technology and Strategy at Ricardo, North America. Little background on myself. I started more years ago than I wish to remember, but it must be like 30 years now at Land Rover, working on Range Rover products, before working for a technology startup in the transmission world and then joining Ricardo. I started in Ricardo UK, working in transmissions, before helping out in the Ricardo Germany office and coming over here to America 6 years ago. I'd now like to introduce my colleagues. So Rod, please introduce yourself.
My name is Rod.beazley. I'm Director of Technology and Strategy within Chris's group. So I have over 30 years of experience in powertrain development. As Chris mentioned, we all started our careers in the UK. So I started my career at the Rover Group and then moved on to work for a number of engineering consultants and then joined Ricardo in the UK in 1996. And in 1999, I had the chance to come to the US to work on a small concept study for General Motors. I was promised I'd be home for the millennium. 6.5 years later, the project was still going. And so I've decided to stay in the US since. So I recently came back to Ricardo 15 months ago, and I'm now in Chris's group.
Thank you, Rod. And also we have Richard.crossley. Now, Richard is actually an ex-Ricardo employee, but is now a consultant to us with his own company. So Richard.
Thanks, Chris. My name is Richard Crossley. I'm the principal of Crossley Consulting. I've got over 20 years of experience. Started also in the UK with Jaguar Land Rover, at the time owned by Ford, which facilitated a move to the US in 2001. So I've got around 20 years of domestic US experience. During that time, I have had a little bit of global exposure in Australia, working for General Motors Holden in Melbourne. I've also been around a number of other companies in that time frame, including Mahler and Linamar. Started with Ricardo in 2011 and moved on to do other things in 2016.
Thank you, Richard. And last but by no means least, Mr. Barnes.
Hi, thank you, Chris. My name's David Barnes. I've been working for Ricardo now for 35 years. I started out my automotive career at Jaguar back in the UK. Worked there for 4 years and then moved on, ran my own consulting company for another 4 years, and then got invited out to the US to work for Ricardo. And I've touched most parts of the business in my time at Ricardo, but most of my time has been spent in the vehicle engineering group. I'm now working for chris.brockbank in the technology and strategy group.
Thank you, Dave. So today we will cover the requirements for a future truck from now until 2035 and beyond. It's a vision for how the architecture of the truck will need to evolve to manage the challenges that we're going to face in this period. And we'll also cover a few interesting topics such as modular EDU, electronic drive unit, for such a future truck. And we're also going to touch on a very interesting topic, given thoughts today on future fuels. What will the fuels look for? We have a lot of discussion about battery electric vehicles and also hydrogen and hydrogen fuel cell, but there's going to be a significant number of internal combustion engines, but they may not be powered the same way they are today. There'll be approximately 40 minutes of presentations, which will give us plenty of time to respond to questions. So please do send those in. Submit them as we go along in the dialogue panel, and we'll get to them as many as we can towards the end. If your question isn't managed, we will follow up with you on that. And if you're watching this on catch up, once again, please send in your questions. We will reply to them. We want to get around as many of them as we can. So let's start with a little background into Ricardo. So Ricardo is a global engineering and environmental consultancy, and we specialize in transportation, energy, and scarce natural resources. The work extends across a range of market sectors, and that's one of the beauty and advantages of working for Ricardo. You will never get bored. 1 minute you could be working on passenger cars, or it could be commercial vehicles such as this presentation, or rail, or defence, or even motorsport, power generation, or government and government funded projects. We have over 100 years, a century-long track record of delivering projects, and they're focused on innovation and technology. And in everything that we do, our objective throughout that history has been to stick to the ethos of our founder, Sir Harry Ricardo. Sir Harry was one of the most innovative mechanical engineers of his time, very, very well respected. And he set out on a mission in 1915 to maximize efficiency and eliminate waste. And that's what we keep to that ethos today, and it's what we do all through our working lives. So Ricardo, what is it that we do? What is our vision? Our vision is to create a world fit for the future. We cover multiple market sectors, multiple geographies, multiple industries, and it's focused on those 6 items you see on the outside of the circle. Today we're looking particularly on the middle left, air quality and the impact of climate change, what that will do to the truck industry. You see in the inner circle in blue, decarbonisation of transport. You also see net zero energy in industry and mobility. These are the items we'll be covering and working through today. Here in Ricardo, North America, our vision supports the global vision for Ricardo, and our mantra is we are here to integrate a path to a better mobility future. We're starting with today where the new mobility is sort of a concept still, and we'll get to a point tomorrow where we have new mobility at scale. We're going to found this on a few principles of consulting, design and development, and niche assembly. But you see that going through this chasm to cross, straight away we have advanced propulsion systems. And that's going to be the main topic we'll go through today. But also software and controls will be touched upon. Thermal management is another major issue, and eventually we'll get to this point of the zero carbon mobility. Ricardo is 3,000 people strong. But here in the US, we are based in our Detroit Technical Center. We also have an office, satellite office in Chicago. We have an innovation center in Silicon Valley looking at advanced concepts and ecosystems. And only recently, we opened a Southern Californian tech center, which is going to be an extension of our test and prototype development site. We also have support in South America, in Argentina, where we're working with a company who's our software development center. So Ricardo, North America, geographically aligned to the market and technology. We've got extensive development experience, and we have nimble, agile development capabilities. I'd now like to hand over to Rod, who will take us through what is required for the future vehicle.
Thanks, Chris. So I'd like to give an overview of the technology requirements and drivers that will influence the future truck architecture. These include legislative requirements, total cost of ownership, vehicle safety, logistics, driving range. All these were considered by Ricardo as fed into what would be our future truck concept. So I'd like to delve into the future emissions regulations in more detail. I'd like to, this table here identifies the changes introduced by CARB and those changes that have been introduced by EPA, and also on pending changes in the future. So let's start with the California regulations. So they are planning to reduce the engine out NOx of the standard FTP and RMC test from 0.2 grams, which it currently has and was a 2010 initiative and approved as a 2010 certification, to 0.05 grams in 2024, and another step down to 0.02 grams in 2027 model year. They've also introduced a new test, which is called low load cycle test, which is engines will run at part load and speed, and they have to have a 0.2 grams NOx in 2024 and go down to 0.04 grams in 2027. This will be particularly challenging for a diesel engine because you have to keep the after treatment warm enough to efficiently convert the NOx within engine out into something cleaner at the tailpipe. And because the engine isn't running very warm, the after treatment isn't running very efficiently. And interestingly enough, based upon some analysis that's ongoing, one of the challenges to overcome this is to overfuel the engine to heat up the after treatment. Unfortunately, that has the negative effect using more CO2. So there's an interesting balance between the two. Again, another idle test has been tightened up significantly from the current baseline of 30 grams down to, in 2027, will be down to 5 grams. To support all these requirements, California also increasing the warranty and useful life of these engines to make sure that the aftertreatment and the NOx emissions is more durable over a longer period of time. So there's a number of step changes, but the ultimate goal, depending on the size of the vehicle, is significant increasing in the useful life and warranty of the product. For Class 8, this will be particularly challenging. So the current useful life for a Class 8 is 435,000 miles. In 2031, this will go up to 800,000 miles, which is particularly challenging. One of the issues associated with this is how will the OEM still be responsible for the product after it's gone to the second and third owner, because it'll still be, within the 800,000 miles useful life and warranty. In parallel to the low NOx initiative that's been ongoing since 2016 and hopefully will be formalized at the California Board Review in August this year, California recently introduced the Zero Emission vehicle for commercial vehicles. And the goal is to have zero emission vehicles on the road in sales in 2024 with a significant ramp up over the next 11 model years. So there'll be a percentage of vehicles will be zero emissions. And then by 2045, will be 100% zero emission vehicles sold in California. In parallel, EPA finalized the greenhouse gas phase 2 regulations in 2017 with an introduction in 21 model year. This will result over the next 6 model years of a 25% reduction in fuel economy and CO2 emissions. In parallel, they recently announced a notice of public ruling for a similar approach to low NOx to California have, but starting in a 27 model year application. That hopefully there'll be more ongoing discussions regarding that NOPR over the next few months, and legislation should be formalized sometime in the next calendar year.
So Rod, it would be excellent if we can have one standard that we go to. You mentioned the idle test. These vehicles, the Class 8s, they idle quite a lot at night to keep the cab warm. We're going to need to look for different solutions.
That's a very good question, Chris. There will be lots of interesting developments over the next few years of how you keep the cab warm on the Class 8 trucks without running the engine. There will be a lot of electrification solutions, maybe looking at a small engine or alternative fuel or things like that, but it's definitely a key area that the OEMs need to focus on. So this is the next couple of slides are some data that was produced by CARB as part of their 2020 mobile source strategy. And basically what this is saying, although California has mandated zero emissions vehicles for a light heavy duty vehicle, which is less than 14,000 pounds, there'll be a huge percentage of internal combustion engines still on the road in California. They might not be registered in California, but they'll be driving on the road in California. And of those, that percentage of internal combustion engine vehicles, a lot of them will be powered by either gasoline or alternative fuels. And a diesel engine, because of the challenges of the after-treatment cost, will be not cost competitive in these smaller vehicles. And so we'll see alternative spark-ignited technologies making a lot of inroads into these vehicles going forward. The same challenge is associated with medium heavy and heavy duty vehicle scenario. Again, one of the interesting slides from this is because of the legacy of the large fleet of heavy duty engines, so this is class 4 through 8, there's a huge infrastructure in place in terms of manufacturing and supply base, and we see a lot of the 2010 cert engines still going through to the middle of this century. And also there'll be some obviously low NOx, and then the federal low NOx will be as well. But we see a large percentage of internal combustion engines all the way through to 2045 and beyond. So really in California, the ice age is not going away any time soon. These larger engines will be mostly diesel powered. There'll be very little alternative fuel currently, because the cost of the vehicle can accommodate the increase in the after treatment costs. But on a smaller price vehicle, as in the previous slide, it'll be very tough to bear the cost of a diesel after treatment in such a solution. I've mentioned in the previous slides the challenges of alternative fuel solutions and alternative propulsion solutions for commercial vehicles. Another interesting challenge out there is the drive to autonomy. Level 1 and Level 2 autonomy has been under development. Level 3 and Level 4 vehicles have been on the road in development vehicles for the last few years. And if you read between the lines, there seems to be a huge investment in autonomy. A lot of the partnerships have been developed, and the goal is to have a Level 4 autonomy vehicle on the road by the end of this decade. And then when will Level 5 autonomy? Will that happen anytime soon? Will that happen in the next 20 years? It's hard to say. You need a crystal ball for Level 5, but definitely there's a lot of focus on Level 4 autonomy. So there is a definite race going on with the OEMs, be first to market, bragging rights of having, a Level 4 autonomy vehicle as a saleable product. At this point, I'd like to hand over to my colleague, David Barnes, who will talk about future truck architecture.
Thank you, Rod. As this clean energy space matures, early adopters have to make some difficult decisions about when to engage with this type of activity. Obviously, there are many incentives around at the moment for this type of clean energy, but the technology itself is not yet mature. So you have a bit of a conundrum around the best time to leap into it. So on this slide, we are showing the target vehicles we've picked with the rank and rate from the scoring that we did. We haven't got a lot of time to go into these in detail, but we'll touch the high and low points here. Obviously, the baseline diesel engine is a very low cost of ownership, but it has pollutants that are likely to be legislated out of the marketplace in the next few years. The next one in line is a downsized spark-ignited PHEV variant. The costs for these are variable depending on the market that you're going to put it into, but it basically falls into a bit of a hole because it doesn't have true zero emission capability indefinitely. The upside of this vehicle is that it's relatively cheap to implement and the technology is mature. CNG and LNG vehicles are also very mature technology. They're very cost effective. They don't have zero pollutants, but they do have a much better emissions footprint than the diesel baseline. And again, cost is they're very cost effective. The CNG refueling infrastructure is in place. The hydrogen internal combustion engine seems on the surface as if it would be a shoe-in, but the reality is that it also does not have a true ZEV footprint. The technology is relatively cost effective to implement, however. And we see this as potentially a very good bridge vehicle. The BEV tractor, obviously true ZEV, so it's got it meets all the requirements for the clean air markets that it needs to go into. The range is probably its biggest issue, and there are people working on those solutions to that right now, but you can't get out from underneath the fact that you need a very big battery, which costs a lot of money. And the fuel cell tractor also true ZEV, as long as you've got well-to-wheel with renewable hydrogen. But from a point of use, zero emissions at point of use, it still fits the requirements very nicely. And again, range is potentially challenging. We've got two more vehicles which we're going to talk about in a little while. So we've got a platoon skateboard and a transformer lifter concept. So we'll come around and talk to those in a little bit more detail later. We won't spend a huge amount of time on this slide because we have limited time available. If you have any questions, please let me know afterwards. The intent of this slide was really to demonstrate that there is no single solution out of all of these that maps all the way from 2020 out to 2030 and beyond. The true zero emission vehicles are on a glide path to competitive pricing. And we believe that there's going to be a space in between diesel and BEV fuel cell for low emission internal combustion engine solutions. So the first slide we have here is a platoon skateboard concept. So it's fuel agnostic. You can build it as a fuel cell vehicle. You can build it as a gasoline or a diesel or a battery electric vehicle. And it could be two-wheel drive, four-wheel drive, two-wheel steer, four-wheel steer. They're designed to be used in multiples, with one as a lead vehicle and the other one as a follow. They could both be remote controlled as well as automated. The benefit of something like this is that you have a common platform. You're driving from both ends of the platform. This works well until you get up to about 18.5 meters, and that becomes the limiting factor. And obviously these are 10-ton units, but you could get away with fewer units and 20-ton capacity. So all of this is very scalable. So another challenge that you run into with this concept approach is that the multiple vehicles tend to have a limited gradeability and breakover angle. So you can see here we've got about a 12-degree grade with 4 units. Obviously with fewer units and higher ground clearance, you could improve that. And the tractive effort in terms of the actual grade is dependent on the motor size, but this is really more to do with the breakover angles and being able to negotiate changes in grade. So this type of approach is already used for transporting very long elements, things like wind turbine blades, for example, where you actually have to steer the rear of the vehicle independently of the front in order to negotiate some of the tighter bends. So the second future concept that we're going to look at is what we're calling a transformer lifter. This is basically intended to be able to move containers using 2 of the skateboard type vehicles, but this time having one of them being operated by a driver and the second one being either remotely or autonomously controlled. Once again, these are totally fuel agnostic, so you can put them in any environment depending on what the legal requirements are. Right. The second variant of the skateboard concept actually allows us to eliminate the load deck completely by having a tractor and a follower unit actually pick up the container directly. And once again, these vehicles can be totally fuel agnostic. They could be autonomous or piloted or remotely controlled. There are some changes that will be required to the container, but these are eminently solvable. That's all I had. Richard Crossley will now lead us into a discussion on the electric drive units. Over to you, Richard.
Okay, thank you, David. And we do see a number of questions coming through. Do keep them coming in, and we'll try and address as many of them as we possibly can towards the end of the scheduled webinar. So moving down a level and looking at the vehicle propulsion system, we decided to initially concentrate on investigation of electrified propulsion in the form of electric drive units, EDUs. So EDUs were selected as they are compatible with a range of energy storage and conversion types, and can even be included in some types of hybrid systems. So this means that they are able to satisfy the needs of the widest variety of vehicles and propulsion power mixes over time, with suitable adaptations can satisfy vehicle needs from today and on into the foreseeable future. When considering the requirements of truck propulsion, there is a large difference in power required to achieve suitable speeds during hill ascents versus the very much lower power required to achieve a cruising speed on a level road. So this power requirement mismatch is an effect that becomes increasingly apparent as vehicle mass rises. Based on this understanding, we decided to employ the use of multiple motors to achieve the overall required truck propulsion power, in order to allow the opportunity to run fewer motors and improved efficiency conditions during the lower power requirement driving scenarios. So in order to establish an appropriate starting point to then use for further iterative investigation using simulation, we consider the needs of a range of vehicles of different weights with varied numbers of driving axles, all delivering similar dynamic capabilities. This vehicle range results in a wide span of power requirements, as can be seen on the first table at the top left of this slide. However, these requirements can be approximately satisfied through the modular use of only a few sort of building block motor sizes used in various permutations, combinations, and that's illustrated in the last column of that particular table. In order to further test and consider the initial motor module sizing, we further considered the range of operating conditions that a large truck may encounter, and this is shown in the second table in the top right. And here we can see that the use of these initial module building block motors can be used in different permutation combinations, again, to quite closely deliver the desired vehicle powers for each operating condition under consideration. Simulation activity is underway, and this may well lead to improved refinement of the selected building block motor sizes, but for now, these selected motor module sizes offer an initial means to derive an EDU and to assess capability and cost attributes. We also show a picture at the bottom there of the slide, which hopefully more clearly illustrates the efficiency benefit that we believe can be achieved by using the modular multi-motor approach, as opposed to just using a single large motor. The picture is of an efficiency map of a suitably sized EDU motor and inverter system, and it's plotted against axes of normalized torque and speed to allow comparison of different size motor capabilities at different operating conditions. In the picture, we show the vehicle operating at in third gear of a 3-speed transmission, and we have chosen to illustrate 3 different road speed conditions with a fully laden heavy truck on a level road. This picture shows that all of the illustrated conditions, the power requirements of the vehicle, are sufficiently low that a single large motor of 525 kilowatts would not be able to operate efficiently in any condition. So it's a key result. It also shows that a single 210 kilowatt machine would be able to operate reasonably efficiently in all of the illustrated conditions. And yet finally, it shows that the 105 kilowatt machine would be able to operate efficiently under some of the selected conditions, but that ultimately it's too small to be able to meet the requirements of the 60 mile per hour condition. So as mentioned before, ongoing simulation activities will be able to quantify the total benefits that can be attained through adopting this multi-motor approach, as well as being able to refine the sizing in order to maximize the potential benefits.
That's really interesting, Richard. But how would you suggest or the operator, does the operator select between each of the motors, or is it an automatic system?
It's this is essentially opaque to the user operator. Torque demand is received by the vehicle in a very standard way through the throttle pedal, and is dealt with through the control and calibration system to find the optimal combination of system engagements to deliver the desired torque demand.
Great, thanks.
Another important consideration with the EDU is the mounting and integration of the EDU into the vehicle chassis and driveline arrangement. In order to select a suitable mounting arrangement, we initially identified and considered a wide range of possible mounting solutions, and these are shown across the top of each of these columns in this table. These are not intended to necessarily be an exhaustive list of all possible mounting arrangements, but more of a summary of potential families of mounting configurations. We then defined a number of important attributes that could be used as a means of scoring and ranking these different mounting solutions in order to select a mounting arrangement to take forward for further EDU packaging study and development. These attributes are shown as the headings of the rows on the left side of this table and are shown in order of perceived importance from top to the bottom of the table. You can see we have then used a simple red, orange, green scoring criteria to mark the candidates, and wherever the score is not green, a comment is added to the box to indicate what the area is that is considered to cause the reduced score. Given that the key attributes are the cost of the system and the energy efficiency of the solution, the 3-in-1 solutions and solutions avoiding the use of bevel gears tend to score well. So the axle mounted, transversely oriented EDU mounting arrangement, which is highlighted by the green ring on the table, was selected as the mounting configuration for which an EDU solution would be derived. And as you can see, also from the amber highlighting rings on the table, the other transversely orientated solutions also scored quite well, and it would be relatively easy to adapt an axle mounted transverse 3-in-1 solution to either of these other 2 configurations should it become necessary to do so. Based on the selected directions I've described on the preceding 2 slides, we created an EDU arrangement to accommodate modular multi-motors whilst meeting the packaging challenge of a 3-in-1 solution, directly axle mounted and in keeping with a tandem axle chassis arrangement. Further to the motor power, in order to meet the total tractive effort requirements of the vehicle, it is desirable to have multiple transmission ratios available in order to be able to use lower cost motor designs, which don't have very high torque capabilities and in making use of the transmission ratios to provide torque and speed multiplication as necessary. Ongoing simulation activity will help determine the appropriate balance of motor form factor and hence the resultant efficiency map and transmission ratio and ratio number selection. However, an initial EDU arrangement has been created here, which is based around that 3 transmission ratios and the coaxial packaging of the 2 motors previously mentioned. The pictures on this slide illustrate the 3 available transmission ratios and give you an overview of the intended arrangement and the power flows of the EDU. In this arrangement, the gearing has all been selected as parallel axis in order to maximize power transmission efficiency. The system is currently shown with 3 ratios, but could easily be converted to 4 ratio arrangement should the ongoing simulation activity demonstrate that an overall cost benefit is achieved with that move to 4 ratios. The overall ratio required between the motors and the wheels, which is dependent on the selected motor operating specifications, is achieved with ratio steps which offer the required reduction ratio, as well as managing to sympathetically combine the required shaft center distances for packaging benefit. In terms of the transmission itself and the ratio selection, in order to focus on low costs and to maintain transmission efficiency, AMT style transmission shifting is envisaged. However, with suitable integration of further selecting elements, it is possible to ensure supported shifting is feasible. So when one motor is disconnected to engage with the next required ratio, the remaining motor and/or axle can continue to provide propulsion and may even be able to temporarily boost its output to enhance the propulsion support offered during shifting. Likewise, when the other motor or axle follows suit and shifts to the new ratio, the first motor or axle can then offer propulsion support as required. This additional selection element or elements can offer the flexibility of enabling operation using either motor individually in any ratio in order to achieve the improved lower power operating efficiency described previously. Again, further simulation activities will help to determine the cost versus benefit of the improved operating efficiency, which is enabled through this increased operating flexibility versus the cost of the additional selected components. And so here, very briefly, this slide really just shows how the EDUs are expected to package in the tractor architecture. Clearly, there is work yet to be done, but the overview should be clear from these conceptual layouts. We're just showing the coaxial arrangement on the motors and packaging of the EDU components between the rails. It's exactly what David has already shown. So given that the machine and power electronics topology is critical to the specification of an efficient, reliable, durable, cost-effective EDU system, we want to define an achievable technology roadmap through to 2035 to underpin our system assumptions. In evaluating the roadmap, we take into consideration the key attributes of cost, weight, and package size, where weight and dimension roll up to a power density metric in each case. Acknowledging the prevailing drivers for each stage of e-machine evolution through to 2035, each evolution is underpinned by advances such as axial flux machines with high reluctance design, allowing high-speed operation and the enabling of direct cooling of active components to achieve better thermal management, which is key to the delivery of cost and size reduction in the machine. Coupling these technologies with developments in advanced materials such as electric steels, high temperature superconductors, different magnetic materials, insulation, bonding, coating processes, along with advanced manufacturing processes leveraging 3D modeling and printing, provides incremental realization of the required future state. As such, the cost per kilowatt will be more than halved by 2035 from the 2015 baseline, with power density more than tripling by either weight or size criteria in the same time frame. Assuming the realization of all aforementioned concepts, materials by 2025, it is assumed by Ricardo that the use of synchronous reluctance machine topology will be prime. This is a technology which is applicable for a future truck application due to its competitive advantage of low cost, good efficiency, and its independence from rare earth magnets, which are an ongoing concern for supply continuity. Okay, so moving focus on to power electronics, which has a similar roadmap and is taken from the same reference points and with the same objectives. One of the most important enablers is the use of wide bandgap semiconductors, devices such as silicon carbide and gallium nitride. Devices using these chemistries add an essential step in energy efficiency with a corresponding reduction of cost due to their ability to run at higher voltage, at higher switching frequency, and at higher junction temperatures, yielding smaller and more efficient power electronics packages. Higher switching efficiency allows significant reduction in the size of passive components of the system, such as low-pass filters and the isolation of transformers. Operating at high voltage, for example, 800 volts for automotive applications, and using multi-level inverter topology will reduce the size of active components, which are switching devices, and will aid in the reduction of wire or cable diameter to offer a size, weight, and also cost reduction in the power electronics system. Operating at higher junction temperature will reduce the size of the switching devices significantly also. Coupling these advantages with the implementation of advanced cooling strategies, such as direct dielectric cooling, will reduce the size of switching components and heatsink, and will bring down the cost substantially. Ricardo recommends the use of silicon carbide technology for the future truck program due to the availability of devices at high voltage being approximately 1200 volts, and high operating efficiency with technology maturity. We move on to the last slide of this section, which is about EDU cooling, focusing on e-machine and power electronics elements. There are many techniques and technologies available to give effective and efficient cooling of the power electronics and e-machine within the EDU system as a whole. One concept which is being demonstrated by Ricardo is the use of transmission oil to cool the e-machine and the power electronics stack. So oil from the heat exchanger would be directly fed into the power electronics to provide lowest available fluid temperature for temperature stability of that power electronics stack. The same flow is then used to cool the e-machine winding and magnets, which reduces the oil pump flow requirement. The flow is only then used to lubricate the transmission shaft bearing. So in using the same oil path for the transmission system, you end up with the residual transmission loss as the oil itself has reduced viscosity due to its higher input temperature, which is of some advantage in terms of integration. Using a dielectric fluid to cool power electronics yields an advantage of reducing thermal resistance, which can enable the removal of the printed circuit board layer from the design, and could also allow the removal of high voltage wiring. Thank you very much. I'll now hand you back over to Rod.
Thank you, Richard. So as Richard mentioned, I'm going to focus on renewable fuels and what role they will play in heavy-duty combustion engines going forward. There is no doubt that battery electrification is the most efficient way to store and convert energy with minimal losses. But Ricardo feels for a heavy-duty application, there is still a role for the internal combustion engine within the commercial vehicle sector, even out to the middle of this century. The internal combustion engine will be significantly different from today's engine we know in commercial vehicles, and there'll be some radical changes in architecture envisaged over the next 20 to 30 years. The legislative requirement to reduce CO2 and toxic pollutants in the US will further drive improvements in diesel technology. Electrification will play a role in certain vehicle applications where policy mandates or it makes economic benefits for the customer. And there's definitely a play for homegrown fuels like ethanol or low carbon fuels like natural gas in future vehicle architecture. Ethanol is a US fuel that has the greatest potential for growth. Every year, more and more arable land is laid fallow and not worked. For information, in the early days of the E15 study for light-duty applications, Ricardo were very heavily involved in the analysis going forward. Ethanol and natural gas fuels provide significant opportunities for future powertrain developments because of their high octane rating, which allows considerable improvement in performance without any detriment to the base engine. In the case of natural gas, with the low carbon chain, this fuel provides considerable CO2 benefits. There is no doubt from an environmental perspective, the carbon reduction needs to continue. But there are a number of key questions that are not fully answered. How are we going to account for carbon in the future? tank to wheel, or well to wheel, or even full life cycle analysis? Will future electric vehicles meet all the customer needs for all commercial vehicle applications? And the maturity rate of fuel cell applications? And will a fuel cell application be economically viable for all truck applications in the future? There are a number of key attributes that influence the purchase of commercial vehicles: vehicle driving range, payload trade-off, refueling time and productivity, and total cost of ownership. An optimized combustion engine can easily meet these attributes by running on either zero or low carbon content fuels as a single propulsion solution mover, or as a downsized engine solution in a hybrid application where zero emissions is required under certain operating conditions. In comparison to other technology solutions, internal combustion engines are relatively cheap, very robust in extreme operating conditions, and they're supported by a large global manufacturing and supply base, which have very little constraints in terms of rare metals. There are three broad types of renewable fuels that serve the low carbon pathway. Two of these fuels are biomass. First generation biomass fuels are crop-based like ethanol, which is well established in the US and has untapped potential for significant growth if the market demands. Crop-based biofuels only use the carbohydrates within the feedstock during the fermentation process, and the protein is removed during the process and used for livestock feed. Second generation biofuels are from non-crop-based biomass, like forestry residue and waste products such as cooking oil. Biofuel production uses biomass, electricity, and mechanical or organic processes. Synthetic biofuels involve gasification or steam reforming of the biomass to produce synthesis gas consisting of carbon monoxide, hydrogen, and carbon dioxide. This can be then processed to produce combustion fuels. Biofuels have the potential to be highly positive for carbon reduction of the existing fleet because of the relatively ease to be drop-in fuels. But without a change in carbon accounting, biofuels will have the challenge to be a long-term sustainable fuel. Electrofuels, which do not require biomass to provide carbon, in some cases carbon is introduced through a waste carbon dioxide stream from an industrial process or direct air carbon capture. Electrofuels ramp to scale is challenged by efficiency, implementation ramp up, and capital cost associated with the fuel manufacturing plants. Significant policy support is required for full implementation. Two electrofuels are carbon-free on a tank-to-wheel basis. These are hydrogen and ammonia. Renewable fuels need to be carefully selected as they can be expensive to produce in terms of energy required to produce against energy be available for conversion to propulsion, and may be advantageous in terms of CO2 of the energy required to store, manufacture, and transport the fuel. This graph plots the two parameters, energy cost per energy stored on the x-axis and well-to-tank greenhouse gas emissions on the y-axis for a particular fuel. Fossil fuels are a low energy fuel to extract and store and a low well-to-tank greenhouse gas production. But when a fossil fuel is burnt, the extra CO2 is released into the atmosphere and is a net addition for the atmosphere. Whilst biofuels and electrofuels combustion, CO2 is not treated as a net released, as the carbon has been relatively recent captured in the biomass. Second generation biofuels have a wide range of energy costs and CO2 emissions. Least costly are those made from cooking oils. Electrofuels pathways are low carbon and highly energy intensified. The simpler the molecule chain, the lower the energy cost. Hydrogen and methane variants look particularly attractive. There will be a significant competition between land-based transport, aviation, and marine, especially as the latter two have very limited alternative options because of their extreme mass and volume constraints. So what does the future look like in regards to achieving zero carbon emissions, including the use of combustion engines? The axis of this graph is time along the x-axis and tank-to-wheel CO2 on the top half of the y-axis and well-to-wheel CO2 on the lower y-axis. Diesel products, in the top left-hand corner there, will be able to meet the EPA 2027 model year greenhouse gas targets. But bear in mind, based on earlier discussions, they're going to be seriously challenged to meet future toxic pollutant requirements without a significant investment in both product development costs as well as end product costs. Initial estimations from some CARB analysis is there will be a 10% increase in vehicle price to accommodate the more expensive and complex diesel aftertreatment for a 2027 model year vehicle. A spark-ignited natural gas solution has the dual benefit of easily meeting the 2027 greenhouse gas regulations because of the lower carbon content of the fuel, as well as producing very low toxic pollutants from the tailpipes, which will be envisaged to be considerably lower than the proposed future CARB and EPA emissions regulations. Electrofuels in yellow provide a continual glide path to near zero carbon. One approach could be electromethane dilution of natural gas or hydrogen dilution of natural gas, known as hythane. Full adoption of electrofuels with an appropriate pathway allow near zero carbon emissions. If tank to wheels is the measure, hydrogen is the fuel, and methane could be used, well to wheel was the measure. And blue at the bottom, biofuels can be a near carbon fuel depending upon appropriate carbon accounting. In the US, most of the biofuel and electrofuels will require a spark-ignited engine for efficient operation. And Ricardo expects that an optimized spark-ignited engine will be a commonplace in future truck product portfolios. Some biofuels will still require a compression ignition engine. An optimized spark-ignited engine based upon the diesel architecture will be a future solution where the spark-ignited combustion engine can take advantage of the robust base diesel engine architecture, and typical maximum cylinder pressures will be less than the diesel donor engine. So renewable fuels for future engine architecture are an ongoing research project for Ricardo. The research project is constructed about three main themes. On the left-hand, top left, theme 1, well to tank, reviewing the properties and potentials of the fuels themselves. Moving across to the right-hand side, theme 2, consideration of these fuel properties in the context of different vehicle applications, developing paired solutions for different fuels and vehicle types. So optimizing the fuel for the particular drive cycle or the vehicle application will be key. And for this research, we are considering on-road, off-road, and marine and passenger car. And then theme 3 at the bottom is actually looking at the different technical solutions for on-engine and off-engine fuel systems to meet these requirements for those different market sectors. This graph compares a number of propulsion technologies in commercial vehicles and plots current cost points versus our projection of costs in 2030 for 4 key propulsion technologies. So the 4 technologies we considered are diesel engine-based commercial vehicle, battery electric vehicle, a fuel cell, and a hydrogen internal combustion engine. And definitely in 2020, the diesel engine will be the cheapest application for tons per mile usage. Whilst a BEV, because of the battery costs and the fuel cell costs, will be between 4 to 5, as well as a hydrogen internal combustion engine. But then again, this is all very much dependent upon fuel prices and the dynamic situation therein. But we do see over the next 10 years that this disparity in price will reduce significantly as product ramps up. There's more in development in battery technology. There's more cheaper kilowatts per hour in battery as fuel technology develops. That there will be a point towards the end of this decade where a hydrogen internal combustion engine will be in parity with a diesel engine. So again, the question is, how clean is clean enough? As I mentioned earlier, Ricardo are undertaking a research project to look at a hydrogen-fueled heavy-duty engine, spark-ignited engine. We're thinking, based upon the requirements for engine testing, we think we can achieve a 0.05 grams per brake horsepower NOx out limit, which is very, very clean considering the after treatment will clean up that NOx, which you should be able to get to 0 or very, very close to 0 NOx. Is that enough? Is that clean enough for the US? Only time will tell. But we think, based upon our research, there's a point where there is some opportunities for a hydrogen spark-ignited engine to have significant play. Obviously, one of the challenges with the hydrogen engine is meeting the diesel performance, and there's probably a opportunity to increase engine size because of the challenges of burning hydrogen to get a similar diesel performance. So, there's been a lot of trend in downsizing over the last few years. Actually, for a hydrogen engine, there might be a point where we're upsizing. Obviously, fuel system leakage and explosion risk is a big challenge that will be undertaken in this research project. And another key factor that is well known in the industry and has been experienced by many people over the years is hydrogen embrittlement. And hydrogen can have a negative effect on certain materials. So it'll be key to have during the design and validation process to make sure that there's a good, robust product that meets all the requirements without causing any undue stress to matching components. So I think to sum it up, really, there is a play for an optimized hydrogen engine going forward, and we'll see if the industry picks up on this. But basically, with the legacy of the engine architecture and manufacturing situation, I think there's a position for relatively minimal changes to engine architecture to get a very optimal spark-ignited hydrogen engine. There'll be more on the hydrogen research project in future webinars. At this point, I'd like to thank you for listening, and I will pass over to Chris for questions.
Okay, thank you, and thank you, Rod, for finishing that off. Okay, let's start running through some of these questions that have come in. So, sorry for going between various screens, the fun of working from home these days. Question come in. Rod, when do you think these standards will align? Interesting question.
That's a very interesting question, Chris. I know from attending conferences that EPA and CARB have been working very closely together. And envisage, sometime towards this end of this decade, there will be a consolidation of a common standard in the US.
Okay, I'd love to see that. I'm gonna challenge you to a beer on that one. Sometime in the decade. One for Richard. In Ricardo's testing of the common cooling concept using oil to cool both the machine and the transmission, have any issues been discovered or presented relating to contaminants in the oil?
So in terms of the sensitivity of the entities in that whole system, I mean, it remains that the most sensitive pieces in that train are the bearings. So in terms of incremental challenges that are offered in the coupling of those two elements, there's really nothing over and above normal engineering challenges that would be presented if they were separate. That's in a mechanical sense. In terms of a contribution to contaminants, again, there's really nothing being brought to the party with the addition of that e-machine. There may be some further exploration required around suspended ferrous materials in a high flux environment or near a high flux environment, but these are all issues that are not beyond the will of good application engineering and integration as such. I don't think they will preclude the adoption and implementation of the concept.
Okay, thank you. Dave, quite a bit of interest in the skateboard. Sorry, the modular units you were putting in there. One of the first questions you put multiple units. We're talking about multiple units going in for bigger vehicles. Can it scale down as well?
Oh yes, and undoubtedly. I mean, the multiples really works better for a typical ISO container type application, but I could see quite clearly as you transition this to more local delivery rather than sort of OTR applications, I could quite usefully see a single unit maybe with a smaller trailer, so you're not clogging the roads up with a massive Class 8 vehicle with one box on it. But I think given that there are going to be some package constraints around range as you try and compress the package, I don't see any reason in principle why this couldn't go from sort of class 4, 5 all the way up to class 8, and part of that is due to your ability to scale and use multiple platforms.
Okay. The question, let's do that. Could it be used with a downsized regular tractor as a pusher on the trailer?
Yes, I don't see any reason why not. There's two potential options for that. The first is that it's just basically a range extender. So it's a big ass battery with some wheels on it that you connect to a full size BEV tractor unit, or alternatively, you could use a downsized tractor and apply a second drive unit at the rear. So you have the benefit of downsizing your powertrain on the Class 8 vehicle without necessarily compromising the ultimate load capacity.
And I suppose there you could actually be looking at a smaller tractor unit, because as your loads go up, you don't have to size any of the brakes or any of the items for the ultimate capacity, because you can put more and more of these bogies or skateboards in underneath.
Yes, I think with a downsized tractor and multiple bogies, you would probably have to be a little careful around the foundation braking. But I think for the most part, the principle scales up and down with just some, as Richard alluded to before, there's some basic engineering challenges which are eminently solvable.
Okay. Mark has asked, I'll take this one, can we really hit level 4 automation without significant development of infrastructure hardware? And who's going to pay for it? While that came in, I've been out asking our experts in that area, and Madison has come back and said that yes, the commercial vehicle and passenger cars are completely different use cases and will require different infrastructure levels. But there's an awful lot of work on smart city initiatives, and in working proving grounds are coordinating with the city governments. For example, San Diego Proving Grounds runs a Department of Transportation and program, and they're creating the innovation to better understand the technology and the infrastructure investment and city planning requirements to achieve the level of autonomy. So yes, there is a huge amount of investment, but it's educating cities, government, and the public, and all of that will be part of the funding. So long answer to a short question saying, yes, it is going to be expensive. I was on a SAE webinar the other day, and the mention was it's going to cost $1 billion to develop level 4 truck automation, at least $1 billion, which, yeah, lots of money, and we need to do it. I'm just running at the questions. The questions are coming in. We are getting close to our hour, but we will keep going through a few more questions. So if people want to drop at the top of the hour, you can do. Keep the questions coming in. If we don't get to the questions, we will answer them as well. Let's just take one here. I think we've already answered the question from Julian. Could you put an additional unit on the trailer? I think
yeah, I think we've kind of covered that one. But yes, there are some engineering challenges, but the topology is eminently reusable.
Okay. One more question. Let's have a look at. I'm on for Rod here. Hang on. Let me think. Rod, what will be the approximate cost delta increase for diesel-powered vehicle in 2027 model year?
Well, that's a very interesting question, Chris. So there's been quite a lot of analysis going on as part of the CARB discussions with the OEMs, and it really depends upon the size of the vehicle. And people are talking about the delta cost for a commercial vehicle in 2027 model year will be somewhere between 8 to 12%, depending on the class of the vehicle. On a smaller vehicle, a class 3 through 5, that will be a real burden, and as it's such a competitive marketplace to swallow, that's why there'll be alternative, propulsion solutions. But for a class 8, I think, and a 8 to 12% on cost will be acceptable and be able to pass on to the end customer. So it'll be very interesting to see if this reality, based upon the increases in the diesel after treatment requirements and the technology required to meet these future regulations, what is the final number in terms of the component costs. But it's definitely dynamic at the moment.
Okay, thank you. We have got some more questions, but we're going to hold it there, trying to keep it to the hour. So thank you to the panel, much appreciated. Please carry, if you have sent any questions and we haven't answered it, we will answer it by email. And if you're watching this on catch up, then we will please send your questions in and we will respond to those as well. Our next webinar is in 2 weeks' time. It's related to one of the questions that was asked today, and the title is to activate your connected vehicle data. Expanding that into extending the vehicle life, increasing owner-operator satisfaction, and eliminating warranty hits to your bottom line. So that will be the next webinar we have in 2 weeks' time. I thank you for attending, and I thank again our panel. And any questions you have, please email them in directly to us on the emails you see on the screen now or through the webinar. Thank you very much, and bye-bye.